So the provider is interested in performing a study of the drug's effects and needs to know how many patients should be included in the study. So in this part C problem, N is unknown. How many patients? N is unknown. I don't know what my sample size is. The provider decides that 90% of the time, the mean systolic BP in the sample of patients must not rise above 122. 122. And this is X bar. It's saying the mean must not rise above 122. How large a random sample is required so that 90% of the means in samples of this size will be 122 or lower? How should I begin to do this problem? Any ideas? If this is 90, this is 10. And they're telling me that the cutoff for the top 10% is 122. So of course I should start with Z, right? I can't do anything with X and X bar until I know the Z for it. So let's start with Z. Here's Z. 90, 10. Could I possibly have this cutoff? Can I get this cutoff under the Z curve such that 10% is to the right of it? That's another way of saying P90, right? What's P90 for Z? What's P90 for Z? '90th percentile. What table should I go to? Listen, you're dealing with area in the tail of 10%, right? Anytime you deal with area in the tail, you go to what table? T table. So T table, I go to the row for 0.10, and I will go all the way down that. I go to the column for 0.10, and I go all the way to the last row for Z. 0.10 column. You should see 1.282. Do you? Okay. So under the Z, P90 is 1.282. So now it's just a matter of changing this 1.282 back to an X bar. So 1.282 is Z equals X bar minus mu. Mu for this problem was 120, wasn't it? Divided by what? Divided by what? Right, 10 over rad n. Sigma over rad n. But I can't use sigma over rad 25 like I was in the previous parts because n is not 25. N is the unknown. So the only unknown in this whole equation is n. So I have to leave it the way it is. Now cross multiply. So 1.282 times 10 over rad n plus 120 equals X bar. So 12.82 over rad n. And X bar, don't we have a number for that? 122, right? Equals 122. So 12.82 over rad n equals 2. 2 rad n equals 12.82. Rad n equals 6.41. Square both sides, you get 6.41 square equals, I think, 41.08. Yes? Check that. Check me, guys.
41.0881.
Okay, 0.88. And therefore, I can't leave it as non-integer, round up to the next integer. Because this is a sample size, they don't come in non-integer values. Let me move my paper. So this would be n equals 42. So for this one, you actually have to understand what's going on. You cannot just stick it in your calculator and go inverse norm or something like that, because it's the unknown here is n. So you have to solve. Please ask me if you're confused. Can you find me P80 right now for this problem? Please find P80 if n is 42. So I have an x bar. I'm looking for P80. So I have two ways to do this. I could do my calculator, which is inverse norm. 0.8 is the percentile, 80 percentile, comma, mu. Mu is 120. And standard deviation is 10 over rad 42. Sigma over rad n. To do this by hand, you would first go to the t table. Go to the column for 20% on the t table. Go all the way down. What do you see? 0.842 or something like that? 0.842. So 0.842 equals x bar, which is unknown, minus mu is 120 over 10 over rad 42. Cross multiply and solve. So 0.842 times 10 over rad 42 plus 120 equals x bar. That should give you the same answer as inverse norm. So you have choices. Choice A, choice B. Same answer. Agreed? Is it the same answer? Can we check it out?
It's off by the thousands, by like 1.1.
Yeah. So what is the answer for inverse norm?
121.2936. So basically the same.
And this one?
121.2992.
Right. No big deal. 299, either way. 121.299, right? Any issues? Questions? Okay. Let's talk about your extra credit. So we had a couple of formulas last class, and they said that E of x bar, that's the mean of the sampling distribution, is equal to E of x, which is mu. So this E means expectation or expected value, right? Expected value. It's saying that the mean of the distribution that I created, the histogram of x bars, is equal to the mean of x, which was mu. And then I had one formula that I showed you last time. Sigma x bar is equal to sigma x over rad n. That's the standard error, otherwise known as SEM, standard error of the mean, is equal to the sigma of x divided by rad n. This is the formula in the case of infinite populations, infinite n. N is equal to infinity. Capital N. What is capital N? That's the population size. That's the formula you've seen already. There's another one that applies to finite populations. Sigma x over rad n times radical n minus n over n minus 1. And this is for finite n, where the limit as n goes to infinity of this n minus n over n minus 1 is just 1. So what I'm trying to say is that if you take the limit of this term right here, this will drop out and become 1. And that's how you get this formula for infinite n. Take the limit of this as capital N goes to infinity, and you will get this because this becomes 1. So for the extra credit, I would like you to show this for a small little population. I'm going to explain that to you. This, by the way, is called the finite population correction factor. The square root of rad capital N minus n over n minus 1. That's called the finite population correction factor. So for example, if your capital N is 100 and your lowercase n is 8, then that would be radical 100 minus 8 over 100 minus 1. Radical 92 over 99. Where this is the population size, capital N, and this is the sample size, n. So talking about the extra credit, here's the assignment. I would like you to start with 5 objects. Capital N equals 5, so that's the size of your population right here. N equals 5. 1, 2, 3, 4, and 5. Let's work with this right now. Capital N equals 5. You have 1, 2, 3, 4, and 5. What is the mean of 1, 2, 3, 4, and 5? What's the mean? 3. Mu equals E of x is equal to 3. And what is the sigma? Sigma x.
1.414.
How do you know this?
I did this one.
You stuck it in your calculator?
Yeah.
Okay, so I can go stat, edit, put these numbers in your calculator, into calculator, and then stat, calc, so into calculator, into list 1, let's say, into L1, and then stat, calc, one variable stats on L1, and it will give you the sigma x. That turns out to be something, right? You'll figure that out. I would like to now take samples of size 2 from this population with replacement. Do you remember when I was talking about the trout in the Delaware? I was taking samples of size 100 trout and taking their mean and collecting all those X bar values. I want you to do the same thing, but instead of samples of size 100, you will take samples of size 2. And we will do it with replacement, because when you sample with replacement, it's tantamount to talking about an infinite population. So with replacement for infinite populations. And when you do it without replacement, you will get results for a finite population. So I am going to sample from here, where the values are 1, 2, 3, 4, and 5, with replacement. Can you help me? Samples of size 2. 1, 1. 1, 1 is a possibility because the first one is being replaced. Next one, 1, 2. 1, 3. So I kind of set you up. If you look at the page 2. 1, 1, 1, 2, 1, 3, blah, 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 blah. How many values will there be, do you think? I'm going like this. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. 25 values, correct. Next, I want you to find the X bars for all these 25 samples. So, easy enough. Let's find X bar. What's the X bar of 1 and 1? 1 and 2? 1.5. 1 and 3? 2. Do that. Now you will have 25 X bar values, right? Gather them up, stick them back in your calculator, and find the mean E of X bar and sigma of that list. So you will have a list of 25 X bars now. X bars, 25 of them, right? Stick these in your calculator and find the mean of these and the standard deviation of these. And show that this comes out to be sigma x over rad n. Your n is 2. That should take you less than 5 minutes, right? All you're doing is finding these 25 means and sticking those 25 means into your calculator. But once you do it, you won't forget this formula that E of X bar is exactly the same as mu. It will come out to be exactly 3 because the mean of the population was 3. And the E of the sampling distribution of the means, that mean will also be 3. And sigma of X bar will happen to be the sigma that you found in the first part for 1, 2, 3, 4, and 5 divided by rad 2 because your sample size was 2. Follow me? Next, I want you to do it without replacement. The whole thing should not take you more than 10 or 15 minutes. So here I go without replacement. So now 1, 1 is not possible. I start with 1, 2, 1, 3, 1, 4, 1, 5. And then you see that I jump all the way to 2, 3. I don't have a 2, 1. Why not? Yeah, it's already here. 1, 2. 1, 2, 2, 1 is the same sample, right? So how come I included it here? So, what does that have to do with anything? Why? 1, 2, 2, 1. Same thing. What does replacement have to do? Replacement, I can see if you say 1, 1 is in there, 2, 2 is in there, 3, 3 is in there because of replacement. But what does replacement and no replacement have to do with 1, 2, and 2, 1? You understand my question? I'm asking you, what happened to 2, 1 here? Why is it not listed? Yeah. Somehow? Where? How? Where?
2-1 would be the same as 1-2, right?
So wouldn't this 2-1 be the same as this 1-2?
Yeah.
So what's up with that? How come I did it here, but I don't want to do it here?
Because it's without replacement, and at this point, without replacement would mean that you cancel out repeats, right?
It does? There's some unwritten rule like that? That means repeats are no good if you're doing without replacement? I didn't know that rule. I mean, I see that you guys are looking at it here and saying, oh, when you did it without replacement, you left the repeats out. But is there some rule like that? Why are we doing that?
Doesn't the order matter?
Why does the order matter?
When you do like replacement, the order matter.
No, it doesn't. Okay, let me explain something. Here, there is a 1-1 and a 2-2 and a 3-3, which only occurs one time. But the 1-2 and the 2-1 are doubles here. So some of these values have frequency 1, and some of them have frequency 2. Do you see? In this one, there is no 1-1 and 2-2 and 3-3 with frequency 1. So whether I do 1-2-2-1, 1-3-3-1, 1-4-4-1, so everything will have a double, and there will not be any 1-1-2-2-3-3 that doesn't have a double. Do you understand what I'm saying? So in this one, you can choose to include all the doubles, only backwards, or exclude all the doubles. It won't matter to finding the mean and finding the standard deviation. But here, it does matter because some of them, like this mean of 1.5, will occur for this pair as well as for this pair. But this mean of 1 only occurs one time. So I cannot exclude the doubles in the first step because some values occur one time and some values occur 2 times. So everybody's not occurring the same number of times. So here it matters, you must include everybody and their frequency, right? This guy only happens once. This guy only happens once, but every other pair happens twice. So that mean from every other pair should be included 2 times, but the mean from this one and this one should only be included 1 time. Whereas in this method, since there is no 1-1 and no 2-2, you can either include the 1-2 and include the 2-1, or you can cut to the chase and say everybody's occurring twice. So I'll just skip the doubles. Follow me? That's why I'm skipping the 2-1 and the 3-1 and the 4-1, etc. here. So do this properly, count the number of values properly, not including the doubles, and then go and find the mean and the standard deviation of all of these pairs with no doubles included. And then show me that E of x bar, which is the mean of all these means, 1.5, 2, 2.5, 3, ... Find the mean of all these means. Show that this is equal to mu, which is 3. And show that sigma x bar is equal to sigma x over rad n minus n over n minus 1, where capital N is 5, lowercase n is 2. Show it with your data. Follow me? So promise it's not going to take you more than 5 minutes because you have a bunch of numbers here. You're going to stick it in the calculator and find the mean and find the standard deviation. Yes?
Why don't we have 2-1?
You don't have 2-1 because I chose to omit the doubles. And I can't here because everybody's got a double. So your list with with the mean of 1, 2 and the mean of 2, 1, we'll just have this mean of 1.5 counted twice. So it won't affect this value. But here, I had a 1, 2 and a 2, 1 with the double, but the 1, 1 only occurs one time. So there the mean would be affected. So I chose to include everybody up top, and you can do it with and without the double if you like. It doesn't matter. You'll see that the values are exactly the same. Follow me? Question? I know you do.
So for this one, for the without replacement, we don't have like 1, 1 or 2, 2, right?
No, because you can't put the first one back.
Okay.
Okay, so that'll be 2 points added. Just go through the exercise so that you remember the formulas. That's the reason for that. That's all. Why do you look so unhappy and glum? I didn't convince you? I didn't convince you that this works?
The top part still doesn't make sense.
The top part doesn't make sense?
Yeah.
Tell me why.
Like I don't get how like that's not how like the bottom isn't replacement with like the top part. I don't know.
The top part, if my first value is a 1,
Yeah.
the second value is able to be a 1 because I threw the 1 back.
Okay.
In the second one, I don't throw the 1 back. So 1 comma 1 is not a possibility. 1 comma 2 is, 1 comma 3 is, 1 comma 4 is, 1 comma 5 is. 2, 1 is a possibility. 2, 2 is not a possibility. So if you like, you can include the 2, 1 and the 2, 3 and the 2, 4 and the 2, 5 and the 3, 1 and the 3, 2 and the 3, 4 and the 3, 5. You can include all the doubles if you like. This will still work out.
Okay.
I just chose to throw all the doubles out. If everybody's occurring twice, it's not going to affect the mean. It's not.
Okay.
Try it and see. You'll get exactly the same result. Question? The only thing that's not happening here is the 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5, which happened up here. You can take all the other values and do it if you like. Include the doubles or not, don't include the doubles. I chose not to. With me or no?
So wouldn't that affect the second question? How many such samples are possible?
So if you choose double the amount, you work with double the amount. No problem. Right? I choose to exclude the doubles, and therefore you'll have a certain value. And because it's talking about sigma, n minus 1 will not play a role. It'll just be dividing by n values. Right? So why don't you omit the doubles? Omit the doubles. There's no point in keeping twice of everybody. And get me this. Get me this. Make sure it works. Okay. Let's move on to the next chapter, which is confidence intervals. So it's these notes that I'm interested in. I'm not interested in doing this page because this is a repeat of what we've already learned. Okay? This has nothing to do with confidence intervals. It's just a review for you. So before you come back next time, would you please do this page for yourself, and we will talk about the answers. Just remind me to go over this. Okay? Today I want to start with the next page, which talks about confidence interval. So it comes back to the same question. If I have a population, size n, and mu is unknown for this population. I can take a sample, a random sample, size lowercase n, and find its x bar n. This is the statistic that estimates mu, right? We already know that. X bar n serves as an estimate for mu. This is called a point estimate. So the first way to estimate mu is by a point estimate. So x bar n is a point estimate for mu, this unknown population mean. So it's saying if you just want one number, this is one number used to estimate a parameter. So my parameter is mu, and if I had to choose one number to estimate my parameter mu, of course it would be x bar, because it's the sample average. The sample average is the one number that I would use to estimate the population average. Will I have error? Obviously I will have error. How much is the error? Sigma x over rad n, right? I already know that. So this is a point estimate. That's one way. So that's be one question on your exam too. Find a point estimate for mu. All you have to do is read the problem and pick up the x bar that they give you, and that's your answer. X bar n is always a point estimate for mu. My second question is find an interval estimate for mu. An interval estimate for mu. This is called a confidence interval. It's done at a particular confidence level. So take, for example, you are my population, and I want your weight. I want the average weight of this population because I'm trying to install an elevator outside or something like that. And I want the average weight of my population, mu. It's unknown. Obviously, it's unknown. Otherwise, why would I be trying to estimate it, right? So unknown population parameter. So I'm trying to estimate the average weight of my population. Would it be helpful to come up with an interval estimate that says that the average weight lies somewhere between 110 pounds to 210 pounds? Is that helpful, or would this be more helpful? Here's choice A, and here's choice B. The average weight lies between 131 pounds and 168 pounds. Which helps you zero in more on the unknown mu? Something that's this big or something that's this big? Yeah. So this is A and this is B. B helps me zero in on the unknown mu because B's confidence interval is shorter. So it helps me hone in on the mu better because this confidence interval is smaller. So I choose B. Not only does the confidence interval have to be kind of small, but the confidence level needs to be high. So saying that I am 70% confident is no good. 70% confidence is not very confident, right? So 70% confidence level is not desirable. I want my confidence level to be at least 90%. So I am 90% confident of mu lying in some interval that's not a very big interval, but rather a small interval, and high confidence level is desired. So 90% confidence level is much better than 70% confidence level. Saying that I'm 70% sure that the mean weight lies between 110 and 210 is not saying very much at all. First of all, you're not too confident, and second, the confidence level is so big that you cannot zero in on what the mu is. Okay, so high confidence levels are desirable, and small confidence intervals are desirable. Without further ado, let me give you the formula for confidence intervals. Let's say that I am interested in the 80% CI. CI stands for confidence interval for mu. I'm interested in the 80% confidence interval for mu. The formula is X bar N, that's the sample average, plus or minus Z alpha over 2 sigma X over rad N. This is the standard error that you're already familiar with. Z alpha over 2 is the Z value such that alpha over 2 is the area in the right tail. Remember how Z something is defined? Z beta is defined such that beta is the area in the right tail past that value. So here my beta is alpha over 2. I'll explain further. And this is the point estimate. So it's saying if you're interested in the 80% CI, simply take your Z curve, stick the 80 in the middle like this. That's equal to 1 minus alpha. We know that the total area under the curve is 1. So if 1 minus alpha sits here, that means alpha has to be shared between these two tails, alpha over 2 being here and alpha over 2 being here, for a total of alpha in the two tails. So if this is 80, this is 10, and this is 10%, because I have a total of 100%. That means that I can go to my t-table and look up 0.10 column, and I would have this number. Correct? That's why it's called Z sub alpha over 2, meaning alpha over 2 is the area in the right tail past this number. Z sub alpha over 2. This one is minus Z alpha over 2 because Z is a curve that's symmetric about 0. So what happens on the right side happens on the left side, only with a negative sign. Follow me. So right now, can we go to our t-table and look up the 0.10 number? You will see 1.282. That means this one is minus 1.282. Agreed? So now it's just a matter of plugging in. X bar will be given to you in your problem, or you will be given a sample, and all you have to do is find the mean of the sample. Plus or minus Z alpha over 2, which is 1.282, this whole Z alpha over 2, don't get all confused with the alpha over 2 and get all anxious about it. Just embrace it, because you're going to be dealing with alphas from now until the end of the semester. So this subscript is the area to the right, in the right tail. So that happens to be 10%. So this Z alpha over 2 is 1.282. Sigma will be given to you in your problem. N will be given to you in your problem. So plug in. So the left endpoint of the symmetric confidence interval is X bar minus Z alpha over 2 sigma x over rad n. That's the left endpoint. The right endpoint is x bar plus Z alpha over 2 sigma over rad n. That's the confidence interval, this being the left endpoint, this being the right endpoint. That means the length of the confidence interval is equal to 2e, where this mess is e. The margin of sampling error. The margin of sampling error, E, is denoted by Z alpha over 2 sigma over rad n. So the confidence interval is x bar minus E, comma, x bar plus E. And the length is 2e. Watch me make a confidence interval. I will start with x bar, and I will go a distance of E to the left. That will bring me to x bar minus E. And then I would go a distance of E to the right. That will bring me to x bar plus E. So the length of this is 2e, where E is equal to Z alpha over 2 sigma over rad n. This will become part of your daily vocabulary. It just will, because you'll be doing a million problems. So let's do an example. Example, mu is unknown. But I know that x is normal. I take a random sample from x. Take a random sample from x, and x bar 49 is the size of the sample. N equals 49. X bar 49 turns out to be 108. Sigma x, assume that this is known. Assume that it's known ahead of time. It's an artificial assumption that sigma be known. I'll explain to you why in a minute. Sigma x, assume that it is known, is equal to 8. And n is equal to 49. The question says, find a 90% CI for mu. What are you going to do? Draw Z. Stick the 90% in the middle. What is left to be shared between the two tails? 10% left to be shared. So 0.05, 0.05. Go to the T table. 0.05 column. Go to the 0.05 column of the T table. What do you see? 1.645 and minus 1.645. Because of the symmetry of Z. So I'm looking for a 90% CI. So it's going to be x bar n is 49, plus or minus Z alpha over 2, which is 1.645, sigma 8 over rad n, rad 49, which is 7. Find the E. How much is E? Stick that in your calculator. 1.645 times 8 over 7. 1.88. Can we confirm that number? Okay. So x bar 49 was 108. So 108 minus 1.88 is the left end point, and 108 plus 1.88 is the right endpoint. And this is your 90% confidence interval for the mean. 109.88 and 106.12. I would like more confidence. I would like to find the 95% confidence interval next. The problem is when my confidence level goes up, unfortunately, my interval gets wider. So there's a trade-off. Do you want a 90% confidence interval that's small, or do you want a higher percent confidence interval, but no doubt it will get wider? So as the experimenter, that's your choice. Do you want a 90% confidence interval that looks like this, or a 95% or a 99%? Unfortunately, they get wider as you increase the confidence level. Let's show that, okay? What's the difference? What will be the difference if I change this number to 99%? Then I would have 99 in here, and this would not be 0.05, this would be 0.005, and this would be 0.005, and the only number that would change would be this number, right? Can you go to the 005 column of the T table, and what do you see?
2.57.
Yeah, 2.576. So E will get bigger, and if E gets bigger, the whole confidence interval gets wider, because how does the confidence interval get created? You start at X bar and you go E this way and E that way. So if the E gets bigger, because this was replaced by 2.576 instead of 1.645, if the E gets bigger, then the interval gets wider. So you will have a wider interval than this. Follow me or no? So it's a trade-off. Unfortunately, as the confidence level goes up, the interval gets wider and wider and wider. You don't want a very wide interval, so you have to settle on what confidence level you would be happy with and what size you would be happy with. Any questions? Okay, we'll continue on Friday.
Was the X bar given?
X bar is given, 108, right here, right here.
It was given in the problem, right?
Yeah, it's given in the problem.